Okay, so let's ask the following question. Let's say that okay, we know what a sequence is now, right? We just learned what sequences are. So let's construct a sequence of natural numbers. I'm sure you did things like this in calculus, right? Say yes? Okay. So here is a question. Why does this definition make sense? Why does there exist such a sequence? Let me write down a couple elements of the sequence. We start at 4. We then have 11, then we have 25, then we have 53, and it goes like this. Why does this exist? Why does this definition make sense? And by why does this make sense, I'm actually asking the following question. What is this? This is supposed to be a function from natural numbers to natural numbers, sending 0 to 4, 1 to 11, 2 to 25, 3 to 53. Why does this function exist? Can you prove using the axioms we've seen up to now that this function exists? I'm telling you how it's supposed to behave. I'm asking whether this function exists. Whether this function exists. The answer turns out to be yes, we can prove that, and that's exactly what we're going to do. So, theorem, well, we can prove that this exists, but it's not trivial, okay? It's not trivial to make sure that such a function exists. The recursion theorem. Now, the point of recursion theorem is the following. Whenever you write down, okay, what's one of the objectives of this course? To show you how certain mathematical practices are actually like formalized and justified. In practice, we use these kinds of definitions a lot, okay? Recursive definitions. So why do these make sense? Because of the recursion theorem. Recursion theorem tells us that all that mathematical practice we're doing, like all that recursive definitions that we write down, in practice, they actually make sense. There are functions and sequences and sets and blah blah corresponding to those definitions. Now, recursion theorem has many variants. Because, you see, I'm going to state a version, and with that version you can prove this. But if I put here fn minus 1, an additional term, you can prove the existence of the sequence with the version I'm going to write down. So for different types of recursions, you can prove different versions of this. There is a general version of recursion theorem in the textbook that I talked about, the Introduction to Set Theory. There's a more general version, the version where we have parameters. You can look at the proof of that if you want, but in the lecture, I'm going to do the parameter-free version where you can only do recursions like this. So in the recursion, you're only allowed to look at the previous element, not the elements before that, okay? What does it mean for someone to do recursion? Like, if you're doing recursion, you're basically using the stuff you already constructed before. This theorem will allow us to do recursion where we can do recursion by looking at just the previous element, okay? Not the elements before. But there are variants of this which allow you to do all kinds of recursion that you want. So let x be a set and little x be a fixed element in x. And we have a function. Now this function is supposed to represent the recursive step. What I mean by that will become clear in a second. Let me finish stating the theorem. Then there exists a unique function g from natural numbers to x such that g satisfies two properties. G of 0 is x, and g of successor of n equals f of g of n for all n. Now, what is this? What is this? Say something. This is a set, which is a function from natural numbers to x. So this is a sequence, right? So this theorem, whatever it does, it tells me the existence of a certain sequence. Which sequence? Let's try to understand this sequence. The first element of the sequence is x. The second element of the sequence is, okay, I don't have g of 1 equals something, but I can figure out what g of 1 is. 1 is the successor of 0, so if I plug in 0 here, I have g of 1 equals f of g of 0. G of 0 is x, so g of 1 is f of x. Now I want to find g of 2. Plug in n equals 1. G of 2 equals f of g of 1. So at any stage, in order to find the value of g at some stage, I apply f to the value of the g at the previous stage. So this function g is exactly this sequence. So this is literally the function g whose existence is guaranteed by this theorem, okay? Now, why is this called the recursion theorem? Because, you see, the value of g is computed recursively. In order to find the value of the g at this point, you have to use its value over here. This f it's kind of the recipe. It tells you what to do. You take this value, you apply f to it. For example, if you choose your f to be the function which takes some x and which takes some n and send it to 2n plus 3. And if you choose your little x to be 4. So choose your little x over there to be 4. Choose your f to be n goes to 2n plus 3. We haven't defined addition, but we're going to do it in a second. Not in a second, maybe like lecture. We'll see. So choose your f to be this function. Choose your x to be 4. Then, by recursion theorem, the following sequence exists. 4, 11, 25, 53, and so on. So recursion theorem literally says this sequence exists in this case, okay? Now, as you can see, if I put am minus 1 here as an additional term, then recursion theorem won't apply. Because, as you can see, over here, the recipe f is only allowed to, it's only allowed to look at a single set. And it can only look at the previous guy. Now, if I just put here n, I allow f to look at n many sets. So it can look at all the n many previous sets. So if you want to construct a sequence like this, where you want to use the previous two terms, then you have a different version of the recursion theorem. There are more general versions, as I said. You can find it in the X book. We're not going to prove those, because when you see the proof, you'll realize that this is not easy to prove. It's not that difficult, but it's going to take some time. So we're going to just prove this variant, which allows us to do recursions just by looking at the previous elements, okay? Now, is why recursion theorem is called recursion theorem understood is the connection between this real life example and that theorem understood. You choose your f's appropriately, you set up a starting point, then the recursion theorem tells you that, yeah, you can do recursion, such a sequence exists. So we want to prove this. In the proof, I need to use certain functions satisfying certain property. But that property is too long to write down every time. So I don't want to write let t be a function and 2 lines of properties. So I'm just going to make an auxiliary definition in the proof. I'm just going to make up a definition which is only valid for this proof and define what I'm going to call n-step computations, okay? So let's start the proof by that auxiliary definition. For a natural number n, call a function, let's call this t, from n to x. You see, I have an x, I have a little x, I have an f. Those are fixed. Call a function n-step computation if t of 0 is x and t of s of m equals f of t of m for all no, I want n-step computations, which means that I need to have s of n here. Sorry for this. S of m, blah, 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 for all m in n. Okay? Okay. There are typos in the notes, by the way. You might have realized that, like, sometimes I'm writing things differently because there are typos there. That needs to be fixed. I need to take notes of that. Anyway, so we call such a function an n-step computation. Let's understand what an n-step computation is. I want to prove that such a sequence exists. My idea is to construct this sequence slowly. So I'm going to first construct this sequence of length 1. I'm going to then construct this sequence of length 2. I'm going to then construct this sequence of length 3, and so on. Now, what's a sequence? It's a function from a natural number to a set. If that natural number is n, then that's a sequence of length n. So I want to construct these. So I define, like, I call these guys n-step computations. What do I mean by that? Let's read the definition. An n-step computation has domain. It's a function from s of n to x. So this is now a sequence, okay? This sequence has length s of n. And this sequence satisfies the following property. Its first element is x. Its value at some point is obtained by applying f to the previous value. So n-step computations are exactly these guys. Well, that's a bold claim. Let me say the weaker claim. These guys are n-step computations. These guys all satisfy these properties, okay? Is this understood? So what I call an n-step computation is, it's basically you're just cutting this whole sequence somewhere, and you're trying to, like, characterize these sequences. Which properties do these sequences have? They have these properties. Their initial element is x, the little x, which is fixed, and they obey this recursion rule. Okay? Now, those are n-step computations, but is the reverse direction true? Like, it's intuitively true, right? If you have a function like this, it's supposed to look like this, because it should be a sequence which starts with x, then then you will find f of x, then you will find f of x. So those are supposed to be exactly all n-step computations. Okay, we're implicitly proving what I just said in the course of this big proof. Now, construct G, construct the following set. Okay, there exists some n, t is an n-step computation. Now, I can write this whole property over here if you want. It can be written with a formula in the language of set theory, blah, blah. The point is, I want to apply axiom of separation. So I write down a property. In order to apply axiom of separation, I need to choose my sets from a fixed single set. Now, what I want to do is I want to take all the n-step computations together. I want to put all the n-step computations somewhere. Now, if I just write this, it's not clear that this is a set. It is indeed a set, but why is this a set? Each n-step computation, okay, it's a function. What's a function? It's a relation. So this t is a subset of, this t is a subset of s of n cross x. Well, this is a subset of natural numbers. So all n-step computations come from this set. I'm not saying that every element of this is an n-step computation, but what I'm saying is n-step computations are subsets of this specific set. So by axiom of separation, this is a set. I take the elements of this set which satisfy a certain property. Good. Now, I'm going to do something that you don't see a lot. As in, I mean, if you probably pick some analyst from the department and ask him what this is, like, I'm going to claim that this is a function, and they're going to say this notation doesn't make sense. But for us, as you know, functions are relations, which are sets. This is a set, so this may be a function. Claim. Oh, I really shouldn't call this G, because I called that G. Let's call this big G. Okay? I claim that the union of big G is a function. What does this consist of? G. It consists of all these n-step computations. Yes?
When we consider these t's, are those initial steps are all the same, or it depends?
You mean depending on n?
No, depending on t. We said that t0 is equal to x. For all t in G.
Yeah, x is fixed. X is fixed. All of them start with x. That's important. X is fixed from the very beginning. So, I claim that this is a function. What this function does is, let's understand what's going on. Okay, let me draw a picture so that this makes perfect sense. Then we have to write stuff down to make this formal enough to be convincing to the audience. Tell me a zero-step computation. This is a zero-step computation. Its domain is s of 0, namely 1. Its domain is 1. It sends 0 to x, and it satisfies its properties. Tell me a one-step computation. This is a one-step computation. This is a function from with domain 2. Its domain is 2. It satisfies its properties. It sends 0 to x, 1 to f of x. So it satisfies this as well. This is a one-step computation. Here is a two-step computation. So the domain of this guy is 3. It satisfies this property. Now I collect all n-step computations. So this is going to go on. And I'm going to take the union of this. When you take the union of this, what do you get? You get a set of ordered pairs. What ordered pairs? 0x, 1 f of x, 2 f of x, and so on. So I'm just going to, this union, as you can see from the picture, it's supposed to be exactly the function I'm looking for. Is this clear? These are my n-step computations, 0 step, 1 step, 2 step, blah, blah computations. I'm going to take the union of these. When I take the union of this, I get a set of ordered pairs, which turns out to be the function which sends 0 to x, 1 to f of x, 2 to f of x, and so on. So the union of these guys is exactly what I'm looking for, okay? So let me erase this. The union of these guys, which I'm going to call little g, is exactly what I'm looking for. So let's first prove that this is a function. I need to prove several things. I should first prove that this is a function, then I should prove that it satisfies these properties, and I should prove that it is unique. This is actually important, that this is unique. Now, you may remember, okay, I don't want to erase the statement, but I don't want to jump to that part, so I'm going to erase the statement. You may remember when we introduced functions for the first time, we talked about compatible functions, okay? When two functions are compatible. If they take the same values for points in the intersection of their domain and blah, blah. Then there was an exercise which I believe was here. I said, like, if you have a collection of compatible functions, take their union, that's a function. You remember that exercise? If you have a collection of functions which are all pairwise compatible, take their union, that's a function as well. I have a collection of functions. I want to prove that their union is a function. It suffices to prove that these two guys are pairwise compatible. By an exercise from a couple weeks ago, by some let's say some exercise, it suffices to show that any two elements of G are pairwise compatible functions. Okay? So if I can show that by that exercise, their union is a function, I would be done. So how do we do that? Now, let U and T be computations. Let's say that T is an n-step computation. Well, no, a minus 1-step computation in this case. And let's say that the domain of U is M. Okay? Take two computations, let's name their domains. Because their domains are natural numbers. Without loss of generality, we may assume that M is less than or equal to N. Or let's go the other way around so that I'm being consistent with nodes. Now, one of those natural numbers are the smaller one. Maybe they're the same, but like one of them is less than or equal to the other one. So whichever one that is, I'm going to call that N. Okay? If N is not the smaller one, then I can interchange the places. So without loss of generality, let's assume that this is the case. Then n is actually a subset of m. Now, this requires some thinking. If n is m, then every set is a subset of itself. That's fine. If n is strictly less than m, then I have this, n is in m. Now, this implies that n is a subset of m. This is not obvious. Again, this needs to be proven. Prove that if n is in m, then n is a subset of m for natural numbers. How do you prove this? By induction. Do an induction argument to prove this, okay? I don't want to do an induction within this proof. This proof, I don't want to mess this up one, okay? I don't want a messy board. So prove this on your own time by induction. This happens. If, let's say that these are not compatible. If these guys were not compatible, what does it mean for these guys to be not compatible? There would be some element, let's name this, I don't know. Apparently I named it K prime and n. You see, what's the intersection of their domain? The intersection of their domain is n. So if they were not compatible, there would be some element in the intersection of domains such that they take different values. T of k prime is different than u of k prime. Okay? Now let's try to figure out what this k prime is. These are n-step computations, right? Which means that by definition, they are sending 0 to x. Therefore, k prime is not 0. Thanks. So if these were not compatible, there would be some element in the intersection of their domain so that they're different at that point. They take different values. Well, by being n-step computations, these guys are forced to send 0 to x. So this k prime cannot be x. It cannot be 0. What can you tell me about a natural number which is non-zero? It's the successor of some element. This was the other exercise as I assigned at the very beginning. If this is non-zero, it's supposed to be the successor of some element. Okay? Now, I need to sneak a word in here. Now, what I want to do is the following. Here's my contradiction. That's blah, 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 blah. But as t and u are computations, n-step, and no. But these are like n-step and m-step computations, actually m-1 step and m-1 step computations, but I'm just going to write by assumption. Okay, these guys satisfy the properties of being n-step computation, so they have to satisfy the following. T of k prime equals k prime is the successor of k. Now I have this. What do I know about n-step computations? T of s of k equals f of t of k. Now I want to do the following to get a contradiction. T of k should be u of k, and because this is also an n-step computation, f of u of k would be u of S of k, and this would be u of k prime, which is a contradiction because we just got that these are different. Now, in order to do this, what do I need? This is by being an n-step computation. Sorry, this is by the fact that this is the successor of k. K prime is the successor of k. This is by the fact that it ends an n-step computation. Which fact did I use here? I used the fact that t of k equals u of k. Why is that true? There is no reason for this to be true unless you make sure that this k prime for which these functions take different value is the least such guy. So there would be, that's the word I want to sneak in, there would be at least k prime satisfying this, okay? I'm taking that. Otherwise, this wouldn't work. You see, over here, in order to say that t of k equals u of k, I may have to make sure that they're the same. How do you make sure that this is the same? If you define k prime to be the least number satisfying this, least natural number satisfying this, because k is less than k prime, these are automatically equal. So you need to take the least k prime. This is important. Why does there exist such a least k prime? Because natural numbers are well ordered. If there is any k prime at all satisfying this property, there is a least one. Okay? So I'm also using the previous theorem that natural numbers are well ordered. Now, we have this, which is a contradiction. Thus, u and t are compatible. These are compatible functions. And this finishes the proof that this is indeed a function, this g. This g consists of compatible functions, therefore their union is a function. Now let's continue. The statement of the recursion theorem involves like four important things to be proven. First of all, there is supposed to be a function, which we proved. Second, their function has to be unique, which we're going to prove at the very last. And third and fourth, this function which exists, it has to satisfy certain properties. Now, let's prove those. Oh, no, I have to prove something important before this. No. Let's go back to the statement of the recursion theorem. It was over here, right? You can imagine it. It said there exists a g from natural numbers to x satisfying something. And like intuitively when I drove some pictures and so on, I realized that I need to take the union of these guys. That's the function I'm looking for. I took the union of this, I showed that it's a function. But what's a function? It's a well-ordered relation. Okay, it's a relation which is well-ordered. But I don't require I need more than this. You see, I said g is a function from natural numbers to x. I just showed that I'm claiming that this g is what I'm looking for. I just proved that this is a function. Why is the domain of this thing all of natural numbers? We have to prove that as well. We have to prove that the function g, little g, is a function from all of natural numbers to x. Okay, so this is the second claim. And we're going to prove this by induction. So we shall prove that the domain of G is inductive. Domain of G is clearly a subset of natural numbers that you can just show. Okay, any n-step computation has the domain which is a subset of natural numbers, so you take their union. So the domain of G is a subset of this. This actually even follows from the second part of that exercise about compatible functions. Anyway, we have this. So we need to show that this is inductive. Clearly, 0 is in the domain of G. Why? Because this function is a zero-step computation. Okay? This is a zero-step computation, which means that this guy is in big G, which means that 0 is in the domain of small g. Okay? So we have 0 inside. Now, let n be a natural number such that n is in the domain of G. We wish to show that successor of n is in the domain of G, okay? Now, because n is in the domain of G, by definition, there should be some computation. There should be some computation T such that n is in the domain of T, okay? Because domain of G is the union of domains of these guys, domains of these computations. Okay. Case 1. Now let me look at the successor of n. If the successor of n is in domain of T, then I'm done. Successor of n is in the domain of T. This is a subset of domain of G. Okay? So domain of T is a subset of domain of G. And in this case, we are done. We're lucky. Let's look at the case where successor of n is not in the domain of T. So n is in the domain of T. Successor of n is not in the domain of T, which means that domain of T is S of n. So T is an n-step computation, okay? Now, let T prime be the following function. T union S of n f of T of n. This is a function from successor of n to x. I extend this function to another function whose domain is successor of n. So I just define it at the next integer as well. And I define it in such a way that this property is true. I take the value of this guy at n, and I apply f to it. So think of it like this. This is like if this is the function, if this is the zero-step computation 0x, what I'm doing is I'm adding to this 1 f of x. If this is 0x, 1 f of x, I'm adding it 2 f of x, and so on. Let this be that. Then, okay, I'm just going to be hand-wavy about this part because we don't have enough time. Then this is an S of n step computation. And so S of n belongs to domain of G, okay? S of n is in the domain of some computation, so it belongs to the domain of G. Thus, by induction, domain of G is the whole thing. I just proved that domain of G is inductive. 0 is inside. Whenever an element is inside, the successor is inside. So domain of G is inductive, and hence the whole thing, okay? Now I have a function from natural numbers to x, which does something. Now, that this function does what it's supposed to do, it's your homework, it's exercise. That this function is unique, I am going to prove. So, exercise, show that g of 0 is x and g of s of n is f of g of n for all n in n. The domain of g is everything, so I can check whether g of 0 is x or whether g of successor of some number equals this guy. Double check that this is true, okay? Double check that the function g from natural numbers to x we constructed actually satisfies the properties we wanted to satisfy. So this takes care of the existence of a function which is mentioned in the theorem. But there was a little word in that, like in the statement, the word unique. We want to prove that such a function g is unique. Such a function g is unique. Okay, let h and g be functions satisfying, these are supposed to be functions from natural numbers to x, these satisfy star. What is star? Star is this property, okay? I'm calling those two properties, which is in the statement of the theorem, star. Let h and g be functions satisfying this. We shall prove h of n equals g of n for all little n in n, so that these functions are the same. Now let's look at this statement. Blah, 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 blah is happening for all natural numbers. How do you prove something like this? How do you prove a statement about natural numbers? Induction. So we're going to prove this by induction. Let I be the set of all natural numbers satisfying that. We shall show that this I is inductive. Is 0 in I? Say yes. Yes. Why? Because h of 0 is, by property star, equals x, which is g of 0. Now, let n be a natural number, and let's assume that n satisfies this. Let me look at h of s of n, h of successor of n. By property star, h of successor of n equals f of h of n. Now, because n is in I, h of n equals g of n. So I'm actually using the induction assumption here. H of n equals g of n. So by induction assumption, I have this. Now, h of g of n by property star is g of s of n. And so the value of h and g at the point s of n are the same, and so s of n is an I. Thus, by induction, I equals n. So this is an inductive set. 0 is inside. Whenever n is inside, its successor is inside. So this is all of n. Therefore, for all natural numbers, and h of n equals g of n. So such a function satisfying the property star is unique. Okay? Now the only missing part is it's the exercise part, showing that the function g we constructed actually satisfies this property, these properties. Okay? So do that at home. You can do that easily. It's not difficult. What we have done is, let's go over. We proved that natural numbers together with the membership relation is well ordered, and then we defined like sequences of length n and sequences over indexed by natural numbers over some set. We define n-fold Cartesian products. Those are basically definitions which I might have mentioned earlier, like I might have promised those at some point, like when we construct the natural numbers, we're going to show that a sequence of length n is blah, 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 blah. Now we constructed natural numbers last lecture, so I gave you those definitions. After that, we covered recursion theorem. Recursion theorem, as I said, allows you to construct functions which satisfy a described recursive relation, okay? Now, the recursion theorem we proved only allows you to justify recursive definitions which look at the previous element. Like you're trying to calculate the value of your function over here just by looking at its value over there. It cannot look at other parameters like the element, like all the previous elements, or maybe some sets around not in the sequence. There are versions of recursion theorem which allow you to do all kinds of recursions that we use in practice. We're not going to prove those. You can take a look at the textbook for those. They're proved similarly, by the way. You basically take this proof, like tweak it a little bit to allow certain variations, and it works. The idea is the same. You do a lot of inductions. You construct these m-step computations. You take the union of computations. The proofs are similar, but the statements are different, obviously. So we did that. Now that we have proved the recursion theorem, we can define addition. So next lecture, we're going to prove that 2 plus 2 is 4, okay? We're going to define addition. We're going to prove that 2 plus 2 equals 4, and 2 times 2 equals 4. We're going to prove that addition is commutative and maybe associative. I mean, I'm going to show you how to prove that, how to prove the identities involving basic arithmetic operations, like the multiplication is commutative, but why? You prove it by induction using the definition of multiplication. So I'm going to show you those, and the reason we did recursion theorem before is, as you will learn, as you will realize later, all the definitions of addition, multiplication, and exponentiation on natural numbers, these definitions are done by recursion, okay? So, I'll see you. Have a good weekend.